share this. And cool. So, hi everyone. Have a good evening, good afternoon, good day. It's nice to have you all around. There's a question in chat whether the recording is on. Okay, cool. So I know I can continue. So good afternoon, everyone. It's great to be here. Thank you very much for having me. My name is Natalie Pistunovich, as Grace said, and I'm a lead developer advocate at Aerospike. That's a key value NoSQL database that is really fast and really fun. Some time ago, a friend asked me to help him with a challenge. And in that challenge, I was supposed to see if it's reasonable to try and break through this screen that you're seeing with a CAPTCHA. And without the CAPTCHA, it would be normally just doing a brute force, right? All the combinations from 0000 through 9999. And then you manage to break it. But when you do have a CAPTCHA, you also need to take it, translate the image into text and type this. So you need to prove to the computer that you're not a machine. So this is what I was trying to automate. And this was part of a challenge that was taking place during a conference in parallel to the talks. And that was in kind of step by step. So you finish one step and then you get a tool or something that helps you with the next step. And for those who completed the previous stage to this, received the model that based on which you can translate or transfer this text or this CAPTCHA into a text string. Sorry, somebody hasn't muted themselves, and that's a little bit distracting. Thank you. So I decided that I will try to see, to his request, whether this is something that is reasonable to do in a conference. So within the time frame of 2 hours or so, I will try to do this with Go, which is not the obvious choice for something that is machine learning related, as Python usually is. And then I went through these steps. I took the model, which is, as we said, what you receive upon completing the previous stage. I load it, and then I tried to do an attempt to log in with the PIN that is at the moment. So for example, 2275. I open a cookie jar, I take the CAPTCHA, I translate it using the model, and then I feed it back as a request to the server. And in case the prediction of the CAPTCHA was wrong, you just do again with the same PIN code that you have, because the cookie jar is still running, so everything is good and on your side. And this was a fun experiment. This was a good success. This indeed went into the conference challenge, and this was about 2 hours evaluation of work, or 3 maybe. And I did a pretty extensive write-up about this on the Gophers Academy Advanced blog post. So this is a series of blog posts that used to take place every December. This year it doesn't happen. And I also uploaded the code to my GitHub. You're very welcome to take a picture of this and come back and read if you're curious to how to do this. And if you have any questions, always feel free to write to me. I shared my Twitter handle earlier, and there will be several times that will show up again. So this is Gopher me. I built this Gopher image using the website gopherize.me. This is pretty nice to build your Go avatar. And I am not a machine learning engineer. I'm not a data engineer. I am a backend developer. I studied computer and software engineering, and I did my final project, or the thesis, at university with CUDA. That is the language that NVIDIA developed. And parallel programming was everything I enjoyed, and NVIDIA was the dream job that I had. But then I moved to Berlin. And Berlin is a city of software, not hardware. So I gave up on this idea, and then I went on to work at a startup, and that startup told me that you're hired and you also have to learn Go. So that's how I got into Go sometime in 2014. What's interesting about that company is that they used Go from their very beginning. That was 2013 or so. And at the time, I think it was not even a stable release, but they already adopted it. They're still using Go. They're one of the bigger companies in Berlin who's using Go these days. And from starting as a backend developer using Go, I went on with the years and I found some interest in machine learning, and I gave some talks about machine learning with a bit more focus on this project that I told you about. And then I went on to explore how Go works with infrastructure, and I gave some talks about that. And this talk kind of binds it all together in an interesting way. So there's a little bit of machine learning and a little bit of infrastructure and some maybe backend between all of that. And I hope that there is a good combination in a crowd of people who some maybe come from this background, some from that background. So there will be an aha moment for everybody, but there'll be also a moment of, wow, this sounds really interesting. I'm going to go home and I'm going to read about this more. Well, you won't go home because you're probably watching this from home. Yeah. So if you learn anything interesting, please tweet using the handle of the group, that's Golang NYC. And you're very welcome to follow me if you want to read about other adventures that I have with Go. I am Natalie Pistunovich. So our plan for today is to talk about these things. We're going to cover how to do ML, quickly chat about TensorFlow, then focus on infrastructure for machine learning, covering some different examples, and then some time for questions. So what is machine learning? Looking at Wikipedia, this is the scientific study of algorithms and models where computers perform tasks without explicit instructions, where they just use patterns and inference. And this is a subset of artificial intelligence. What is artificial intelligence? Many things. I found this very interesting picture on Twitter that explains how machine learning is just a subset of AI, and it comes together with things like NLP and speech to text and text to speech and the scheduling and planning and whatnot. And the definition can be that this is intelligence that is demonstrated by machines, which makes it artificial, unlike our human intelligence, which is natural intelligence. And this is describing how computers mimic cognitive functions like learning and problem solving. Okay, so we get a general understanding. We have the definition in mind that always helps to shape up how to ML. With these steps, you start by defining the problem. What are you trying to solve? Is this text prediction? Is it a recommendation? Is it image recognition? And then you gather data that has to be relevant to the task. If you're doing text recognition, you probably want to have only text from your specific language. You don't want to have letters from other languages. And then you take the data and you prepare it. So you clean as much as you can. For example, if it's dark, you want to make it a little brighter. If it's an image, you randomize it, because if you do digit prediction, you don't want the computer to think that after 6 always comes a 7. And you take the data set and you split that into roughly 75% that you're going to use for training and 25% you're going to use for testing. And then you choose a model. The model depends a lot on what you defined in step 1. What is your learning task? Is it prediction, as we said? Is it recognition? Is it recommendation? Is it something else? What is the type of the input? Is it an image? Is it text? Is it something else? And what is the possible number of categories? So this is the possible number of outcomes. If you're doing a prediction of digits, you have 10 possible outcomes. If you're doing prediction or understanding of text in a Latin language, you're going to have somewhere between 20 and 30 categories, one for each letter. If you're doing face recognition, you're going to have some thousands or some millions of categories. And once you have chosen a model, you're going to go ahead and train that by starting to just give it random values and then making iterations. And between each iteration, you adjust the weights. So the numerical value that you give to each arch between the models. And if this sounds familiar to you a little bit, this is also how you solve partial differential equations. And once this looks done, you're going to move to the next step of evaluating the model. And many times at this point, you're going to find out that this is not exactly as it should be. So you're either going to go back to step 5 and train the model on a different data set, or maybe do different type of adjusting the weights, or you even go back to step 4 and you choose a completely different model. And you use the 25% that is remaining from the data set for this evaluation. And once you're done, you're going to go to step 7 and you're going to fine-tune the hyperparameters, which is very similar to what you do in step 5, but this is done manually many times. And then you're all set to make a prediction. So once we get that in mind, we know kind of what is happening, we can talk about tools that are doing this. For example, TensorFlow. This is an open source tool that I really like, and it's an end-to-end platform for machine learning applications. This is a tensor. This is a visualization of how it looks, and a tensor is a mathematical concept where it's a generalization of a vector to a higher dimension. It can be 2 dimensions, 3-dimensional, 5-dimensional, and more. It's used also in physics, not just in math. And a tensor, you can define it with the data type and with the shape. The data type would be, is it a string? Is it a char? Is it an int? Is it something else? And the shape is the number of dimensions and the number of values per dimension. And then those tensors, which represent the data, flow through the graph. The graph is also the model. It's made of a set of nodes. Each node is the mathematical operation that this is the manipulation that you're doing to the data. And at any point, you can inspect the value that is inside the node. So this is the intermediate value of your data. And the output is the result of the prediction. So this is why it's called TensorFlow. Basically, your data, represented as a tensor, flows through the graph, which is how the model is represented. The reasons that I like TensorFlow is that it's community-driven and it's open source. There's other tools out there. It's not the only solution, but it's my personal favorite. It's also becoming friendly for developers. There are tools like AutoML, which is built on top of that, where you basically just drag and drop images and their labels, and it lands you somewhere after this stage. And you pretty much have a model that is ready and already trained on your data set. There is also TensorFlow Hub, which is pretty much a repo for modules. So people who finish their PhD, for example, and have an interesting new model, they just put it there. And with the TensorFlow API, you can consume this model for your project. And this lands you around the stage that you have a model and you just need to do the final training of it. And because it's open source and the license allows, there's many tools that are built on top of it as a black box, and you paid tools or free tools, and you can just use them as is. So we have an understanding of what is ML, we have an understanding of how to do ML, and we have some familiarity with TensorFlow, which is a tool that allows you to do this. But we're here to talk about the infrastructure. This is a great article written in 2015 by a group of Googlers on the problem of hacking up quickly something to support a machine learning algorithm and just put things into production. I really recommend to take a quick picture, write down the name and look it up later. I learned a lot from this, and there's still, most of the content of this is still relevant these days, even though it was 5 years ago. You can summarize this article into several points. And there's a lot more to machine learning than just implementing the algorithm. Actually, about 5% of the code of such a system is the algorithm. The rest is the supporting modules. So from configuration through resource management, through serving, monitoring everything, and the black box, the tiny one in the middle, it's the machine learning code part of it. Let's take a deep breath. From here on, we're going to dive into a lot more examples. I'll try to speak fast, but also clear. And as an engineer, I have a tendency to recommend specific tools. I do my best to recommend open source ones. And these are personal favorites. There's always more solutions out there. And everything that we will see either supports Go or written in Go or both. So the example or what we're going to cover now is basically infrastructure that is 100% Go written. Hadoop. Hadoop is one of the popular tools that have been around for quite a while. It's an Apache project, and it's an umbrella term for several tools out there. Hadoop stands for High Availability Distributed Object. I forget myself. Oh, and it's hiding. That's sorry about that. I will write what it stands for. And it's comprised of several parts. So first is the distributed file system. Then there is MapReduce, which is the algorithm that is pretty much being used that helps you crunch and go through the data in a more efficient way. Then there is the Hadoop Common, and there is Yarn, which is these days is being replaced. And this is a tool to manage your resources. And there's many other tools under the Hadoop umbrella. Then this slide is probably the trickiest one in this entire presentation. And it's a little bit like comparing apples to pears and then adding into this blend papples, which is also called Nashi pear. And I've done my best to simplify, but of course, whenever you have to do simplifications or abstractions, you're not 100% accurate. So take this slide with a little pinch of salt. And data lake is a term that was coined by James Dixon. And it's basically describing something like a database, but it's actually not shaped. So the data comes in the raw shape, and it stores all sorts of data. It stores strings, it stores ints, but it can also store CSV files, images, audio files, and whatnot. And after all those preparation slides, this is the slide. So data lake platform. The ones that you see here, Google BigQuery, Apache Hadoop, Apache Spark, and Azure Data Lake are some examples for a data lake. This is, I want to say one more time that this is more simplified and slightly abstracted. So there will be people who will disagree with this, and that's okay. But for the purpose of understanding generally what is a data lake, the slide is clear enough. I hope everybody would find this okay, and if not, there's time for questions at the end. Next, there is database. Databases we're all more familiar with. The biggest differences from a data lake is that the data is structured in a specific way before it's being stored, whether there's a schema or not. Database stores the data in a way that everybody can access with the same API, and you don't have to remember how to access each of the different file types you have. Then comes function as a service, or serverless, and you have tools like AWS Lambda, Azure Functions, and so on. Then there is data governance. Data governance is pretty much making the data that you have usable, in the sense that you don't store credit card information if you're not PCI compliant, and you only give the different teams the subset of the data that they need, and potentially you even share some of your data as an hashed or masked with a private information of it. You make a subset of the data available to the public so that they can do their own interesting machine learning projects. And then comes monitoring, which is of course super important because you do want to make sure that your system runs well. And putting this all together builds what I see as a bare bones infrastructure for a machine learning application. So let's say you start with some files. We have Parquet, JSON, and CSV files, for example. Step one, data governance. We filter out everything we want to not live on our system. And again, the example, you're not PCI compliant, don't store credit card information. And then comes the part of storing the data. So you can store the data one time in a data lake, so you have the raw data as is, and one time in a database, so you'll have the data stored in a way that you can access it really fast. And then you make a second iteration of data governance. For example, making sure that when you do log lines, you will not expose the phone number of your users, because a developer who's going to do debugging doesn't really need to see the phone number to know whether the system works well or not. And then you take this data and you do the training of your model. And let's zoom in on this a little bit. This lands us at this stage of how to ML. And you can roughly break this down into two types. There's the static one and there's a dynamic one. The static one basically means that you do the training offline and you upload this. And well, it's easy to build, it's easy to test, but the downside is that it only predicts what it knows about. And because you have to take it to train the whole thing locally and then upload this, the update is pretty slow. It's hours or even days. On the other hand, there's dynamic model, which is being fed from the response of the system. For example, again, a finance example, if somebody files a chargeback, says this purchase was not made, then the model is being fed with this information, and then a transaction is getting this new update that this was actually a fraudulent transaction. So of course, the biggest pro of this is that it's likely to make better predictions, but because this is happening live, it's compute intensive, it's latency sensitive, and you're probably going to have to limit the model to make sure that it meets the SLAs. And you also want to monitor that the SLAs are being met and also that the outputs are reasonable. So this is the model part, the training, and then there's model serving. And we're going to zoom in on that a little bit as well. And this puts us at this stage of how to ML. And you can also break this down into roughly two parts, the one that's being done online and the one that's being done offline. Online, the biggest benefits is, again, the more you have real-time information, the better your predictions are. And an example that I like giving is a flower shop that is using the model to know how many flowers should they order ahead to have in the shop. And then you have this pattern that during the week you sell this many flowers, and then at the weekend the demand goes up, so you should always order a little more. And then comes February. And February 11, February 12, you suddenly see some kind of an increase in buying flowers. And if the model is serving this online, so it sees that there's a change in the behavior, it would recommend you to buy slightly more. And then you're lucky because you end up having a lot of flowers available on Valentine's Day and you don't sell out early on your most profitable day of the year. But the biggest cons of this is, of course, that this is resource intense. So you have to make sure you limit that and that you monitor that the resources are being consumed in a reasonable way and that the results are making sense always. On the other hand, there is the offline serving. And the good thing about it, you don't have to worry about the cost because this is kind of like looking in a lookup table, the results. And you always know all the outcomes ahead because you've done the calculation locally. But the downside, if you are a flower shop on Valentine's Day, you will miss out on a lot of sales because it can only predict what you know and it doesn't notice the change in the behavior. So this is the system as I see most basic, without the one most important part that makes sure that it all runs well, the monitoring. It has 8 parts, and this is what I see as the bare bones, but then there is this slide. This is the ecosystem of AI according to end of 2019, so that's 1 year ago, and it has a lot more fields, you know. You do things like AI ops, and you think about the hardware, and then there is streaming and whatnot. There are visualizations, of course, security, search, and so many other things. So this comes to balance that there's a bare bones infrastructure that probably fits for everybody, but of course there's a lot more to add, depends on what you're doing. Then there are end-to-end off-the-shelf solutions. Again, TensorFlow. So TensorFlow Extended actually covers everything from creating the input set that you need to making sure it statistically makes sense, validate that, train, evaluate, and also do the serving. And the serving part, you have 3 tools to do this. There's a TensorFlow serving, there's the JS, and there's the Lite. So there's the regular one, there's one that's dedicated for mobile and embedded devices like a smart washing machine, and one that's dedicated for web. And then comes the interesting part, a concrete example from a real system in production. This one I know from work, so I bring this here, and I find this pretty interesting. So my the previous company that I worked for was a company that did kind of a fraud detection as a service. The customers of that previous company were, for example, online shops. And what they did is that in their shop, you fill out the information, for example, the credit card information, and then they take this and they ping the server, and they get in response, yes, no, whether this is a fraud or not.
PK is closed tomorrow.
Sorry, could whoever speaks mute.
We've decided to declare a snow day tomorrow. Was made for safety.
Thank you. So what happens is that the transaction details are pinging the server, and the server responds with, is this likely to be fraud or not? And the entire business model is built on the fact that this is cheaper to ask us than to get cheated by fraudsters out there for two reasons. Because one time you will have to refund the customer whose credit card information was used in this transaction. And the second time, the seller will have to pay a penalty fee to MasterCard or Visa or so on for not detecting this fraud on time. And also in Europe, there are rules around, since 2019, I think, rules around that you have to make sure you have some kind of anti-fraud implemented in your systems. So there's a lot of sense to have such a system, at least here. And let's go back to the example. So we have some information, we have user ID, we have seller ID and item ID, and the hash of the credit card. And this comes into our system as a transaction. And this is being stored on the database Aerospike, and this is being enriched. Enriched means that the 4 input values that we saw become a huge blob of information that, for example, how long has this user been registered? And this is getting assigned a numerical value between 0 and 1. When 1 is, it's been long enough for us to give the full credit for this probably reliable. But then the next one, for example, how long the seller has been registered. So it's 0, it means that the seller is new, so we have less trust in the seller. And then you deduct as much information as you can, and you build this input feature vector. And the reason that they were using Aerospike for this is that it's just a lot of information and it's done really fast. You cannot calculate this on the go fast enough to meet the SLAs that you have, which is 200 milliseconds or so for the entire round trip from the moment it pings the server until it comes back. So you use Aerospike to get those as data points as an input and create a very enriched set of information, which is the input feature vector, which is then being fed to the machine learning model. The reason that you want to give more information to the model is that it will help you get a more accurate answer. That probably makes sense. If you have a couple of thousand data points, this is more accurate than if you have 4 data points. The model makes a calculation and then spits out a number. And the number is being compared against a dynamic threshold. And if it's above the threshold, this is a fraud. If it's under it, it's not fraud. And everything, of course, is being monitored if this makes sense. And in case there's something like a chargeback, so a client called and said, hey, there was a fraud, this is not my credit card, then this information is being fed back to the model. And maybe this, of course, this applies, this will change the calculation, and this might also move the threshold up or down, depending on how the chargeback information tilted it. So that was a lot of information. Let's try to recap what we saw, because I would love to hear some questions, because whenever you get questions, it means that people manage to understand, and that's great feedback for you as a speaker. So what we saw is what is AI, what is ML, and how to ML. We saw this slide, and we talked a bit about TensorFlow. that this is basically an open source tool where you represent the data as tensors, and the graph is the representation of the model that you have, and the tensor flows through the graph, undergoing mathematical manipulations to the result of the prediction. And we talked about the differences of online and offline training and inference. And we saw an example of a bare bone architecture components, which looks like this. We saw that to balance that, there are a lot of things you can add depending on whatever you do, if it's your project, if it's at work. We also saw a concrete architecture example, which looks like this. And if there are 3 things to take away from this presentation, is that the machine learning code at the heart of a system is just about 5% or less of a system that's in production. The input data is a huge deal and requires a lot of focus. And the most basic steps that are common to practically every machine learning system in production is you take data, you process it, you store it, you use it to train a model, then you serve predictions based on that model, and you monitor everything. Thank you very much. We'd love to chat and hear some questions now.
I've muted almost everybody, so you'll have to unmute yourself before you can ask the question.
Hi, Natalie. This is Rob Sutter. Thanks for the presentation. Any more suggestions or optimizations for the inference stage or applying the model, especially for keeping model size and times down?
You're asking about SLAs and how to meet them, if I understand correct?
Sorry, I realized my microphone was far away. No, for when you're applying your models for inference, not the training stage, but when you're using them in production, specifically for keeping, I guess, yeah, now that I'm asking it again, for SLAs, for keeping size and times within SLAs, or just minimizing size and execution time, running time. Thanks.
Yeah, yes, it's important to meet them. This is a part that I was focusing less than anything else, and I'm afraid I don't have anything smart to say, but most of the models that I saw in different systems, and not just where I was working, but also in my current work, where I was just talking to different clients and asking, what are you doing interesting around machine learning? Many are using serverless. So that means you're deploying this as a function somewhere and just pinging that. So not part of the architecture is probably what I see as a common pattern. No, this is not a detailed answer, but I hope it's somewhat helpful as at least a starting direction.
Hi, Natalie, can you post a link in the chat or something of that that paper that one of your slides showed?
Let me find it. Yes, it's called The Hidden Technical Debt in Machine Learning Systems.
All right, let me do a quick search. The hidden.
I think somebody just posted it.
Oh, perfect.
That was super fast.
Thank you.
Not a lot of questions, I guess.
Cool.
I can talk a bit about the Go user group if you want. We are meeting about 4 hours earlier than this, so it's probably around your lunchtime. If you ever want to visit overseas, please do. We are on Meetup and we meet every second Wednesday of the month. It's a very similar setup to this. We're also having Zoom calls and we have speakers, sometimes from Berlin, sometimes from other places.
Because one question that I had was about data governance, because that's something that my company doesn't really spend much time on right now. So I'm curious, what does that mean for you and the kind of data that you process where you work?
So because the company that I was diving into a lot was doing fraud detection, most of the examples that I have are from the finance world. So the very basic one is this PCI compliance, that you either go through this PCI test every year or you don't store credit card information. But also masking all the PII, because Europe and personal information is a big deal. So you always try to remove as much as possible, emails, and anything that basically can help you find or make one person unique. So that's the full name, that can be the address, that can be the phone number, and combinations of those. And types of data governance. So in addition to not storing what you shouldn't, and in addition to releasing subsets to the as an open source so that other people can use, for example, on websites like Kaggle. You can also do data governance if you have several different teams, and different teams would require different subsets of the data. Let's say the backend team would not need almost anything, but the data science team might need some specific pieces of information that other teams will not need. So you release this subset to this team and you release that subset to that team. And then each team gets exposed to the minimal amount of information that they need to make their work done well, but also filtering out or protecting the privacy of the users as much as possible. Another interesting thing about data governance is what's used for training the models. So let's say you have 5 big clients that give you a lot of data, and you use that to train your model. And then one of the clients is finishing the contract with you and is leaving and says, please remove all of my data. And then comes the question, if you use their data to train the model and you didn't change the model, did you actually meet this requirement of removing their data from their system? And most of the times the answer is no. So you actually should have kind of versioning of the models trained on the different data sets, so that you will be able to remove the data set of that specific client from your system. So those are some points to think about in the context of data governance.
Hi, Natalie.
Thank you.
I had a question that is going to follow up on some of the chat things, which is sort of going back to the Go language. It seems like to me that that Go doesn't, isn't really well integrated with a lot of the hardcore AI systems like TensorFlow or Fast.ai, but it gets used a lot for maybe the data infrastructure. Some of the, I think maybe Pachyderm might have been written in Go, and a bunch of these other things are written in Go. Is that your impression too, or do you actually, have you seen people use Go for machine learning?
So again, going back to the previous company, they are using Go for most of the system. But the way that the company was, or the tech team was built, is that there is a data science team that does their experiments in Python. And then once it's baked enough, this is being translated into Go. So all the data science functions, whenever you add more logic, let's say, this is in the production, it's in Go.
But what's what library does it actually, I mean, because with Python, they can go to NumPy and SciPy or use these other things. And I'm familiar with at least one Go package, but it doesn't seem to be that popular. So what exactly are they using?
I wouldn't be able to answer at this point what exactly they're using, because I haven't been working there for over a year. I don't remember. I mean, Go generally is not so much about using external libraries, but it's a lot about using the standard libraries and utilizing them as much as possible. So this is a little different from other languages. Of course, you will use the library for Docker and whatnot, and you will use a library for TensorFlow, but as much as you can to do things on your own, this is encouraged. This is the Go way. And for TensorFlow, there is a Go API. With that API, you cannot build a model, but that's okay because there's very little correlation between people who are very good in Go and people who have enough mathematical capability to build a model. But you are you are able to take a model and serve it and also inspect it, so kind of understand what it's looking like, right? Like what the tensor, what each data unit looks like. You are able to do this. Well, for that, you can even use the CLI, but you can also use the Go API for this. And you're basically, once somebody hands over a model to you, so in TensorFlow, the models are built as protobufs, then you have everything you need in the Go API to use it in production. It's also worth mentioning that there have been an update in TensorFlow to the recent version, and at the moment it is broken. So you actually, right now, you cannot use this in production unless you're using a slightly older TensorFlow version.
Hi, thanks again for the talk. To continue on that last question, does TensorFlow do, your basic standard, feed forward, your model is basically fully connected and you determine how many, what are they called? Hidden layers there are, like the basic, basic parameters, and it's just a simple calculation to, in other words, in production, you could write your own pretty simply, right? If everything is pretty standard, if the model is I guess what I'm getting at is, what is the model? It's really just how many layers, what's your input, and what are all the coefficients when you've run it through and when you've trained it, right?
Do you even need things like the coefficient actually to run this? Like I think you can do fine without knowing that, right? Like how many inputs and what their types, of course you need, because you have to know how to interact with it. But what it does on the inside, if you can find this out with Go, I'm not sure, I never tried, but for the inspection part, like to understand how to work with a model that is handed to you as a black box, there is a dedicated CLI. And then the output of that is like all you need to work with API. If I got your question right.
I mean, I was just asking, I mean, to the models that TensorFlow, that you would create with, using Python or whatever, what types of, like, is it, can you do, for instance, reinforcement learning, or are there more exotic models, or is it just the standard feed forward model?
There's the TensorFlow hub where everybody can upload a model in the way that TensorFlow APIs can consume it. The representation of them is with protobufs.
Okay.
You can create your own model in Python if you want, and then just in the Python API, there's extra commands to make it the TensorFlow adjustable format, compatible format.
Okay. Thank you.
I think DeepMind is using TensorFlow, so it probably can handle just about any model you can throw at it.
Yeah, I was going to say deeplearning.ai uses TensorFlow for all of their lessons.
Yeah.
So any neural network, it can certainly handle. I don't know how many other machine learning techniques it supports directly.
Thanks.
Any more questions? I am on Twitter in case you have more questions that you think about later. Do feel free to write. The DMs are open. I'm also on the Gophers Slack. If anybody is stepping into Go and is not on the Slack, let me share an invite link. There's a great channel for questions. There's a great channel for beginners.
Oh, we have somebody wanting to know about Aerospike.
That's the one line that I like to use it to describe. It's the fastest database that you never heard of. I only got to know it because I worked with it myself. And when I was moving on to my next job, I approached them and said, hey, I want to work with you. This is a key value. This is NoSQL. This is really efficient, really fast. It has APIs for 10, 15 languages or so. One of them is also Go. And it's being used by huge clients like PayPal, like Snap. I don't know exactly which clients I'm allowed to talk about and which not, so I need a moment to pause. But the company where I was working with them, that was petabytes of traffic every month, and that was really high load. This was SDKs that are implemented in different devices. So in everybody's phones, and they have clients like Spotify, for example, and other clients that Zynga, like all those games, and they would ping the backend where Aerospike was taking all the information and storing and processing it and so on. And that's just really fast, and that somehow always works. That was never a downtime. So I found it to be a fascinating, amazing tool that I never heard about. And I still think this is an awesome tool. I would recommend everybody to go and try it. I am looking up the invite link to join the Gophers Slack. There. I hope this one is work, because I know that one of the recent links was changed. So if this doesn't work, please tell me and I will find another link. Great. Do you know if there is a channel for the New York meetup in the Gopher Slack?
I believe there is. I'm not sure though. Ari